Continuing discussion for equations and inequality solving, we're going to review a little bit on how you solved equations of the type x minus 5 equals 0. So remember, equation solving means undoing. So since you're subtracting a 5, you'd have to add 5 to both sides, and you end up with x equals 5 as your solution. So x equals 5 on the number line is a real number, and you can see that just this one point satisfies this linear equation here, because 5 minus 5 is the only thing that will give you 0. If you consider the inequality x minus 5 greater than 0 and solve it just like you have before, you can see that x greater than 5, so 5, which makes this quantity exactly equal to 0, will not be a solution, and everything greater than 5 is a solution from what you see here. And this is how we've solved inequalities prior to now. We're going to show you another way of looking at the same solving inequality problems. And this particular method may sound complicated for this example, but it might be more useful to you when you get more complicated inequalities. So take a look. When you look at this number line, this 5 is right now dividing the number line into two parts, below 5 and above 5. The only point that makes it exactly 0 is the 5. So we have to exclude that for our particular inequality here. So for the second method, what we're suggesting is that you take, instead of solving the inequality, you solve the equivalent equality. So replace the inequality sign with equality, solve just like before. So add 5 to both sides, and you'll end up with x equals 5 as a solution to this equality. Then you can see that 5 minus 5 makes exactly 0 and does not satisfy this inequality. So you have to punch a hole at it because 5 is not part of your solution. What we're saying is that now either the solutions are down here or up here, and we have to figure out which ones. So to figure that out, take a test point below 5, say any number, any real number. So say 1, plug it into the inequality that is given to you, and here we get 1 minus 5 negative 4 greater than 0, which is a false statement, which means that 1 cannot be part of your solution to the inequality. Why is it enough to just test 1 and not all the infinitely many numbers that are under 5? Take a look. We're going to give you a simple explanation here, but there is a much more complicated explanation called intermediate value theorem, which we don't have the scope to go into here for this particular class because it's much more advanced explanation. But you can see that if you take any number, any real number smaller than 5, subtract both from 5 from both sides, and you'll end up with always numbers that are smaller than 0. And that would not be the case for our solutions because you want bigger than 0 numbers. So every single number that you pick from below 5 is going to produce a negative number. So no real number below 5 works. So that's why just taking one test point is enough, because all numbers have the same, will keep the same sign. They'll always give you a negative number. Same thing happens if you pick a test point above here, say 7. 7 minus 5 is 2, and in fact, no matter what number you pick, as long as it's bigger than 5, subtracting 5 from it will always give you a number bigger than 0. And so you'll end up with a true statement, no matter what real number you pick, that is above 5, and that's why that is part of your solution. And of course, don't forget, we can write our solutions in interval notation, which would be 5 to infinity. This may sound like a complicated method to solve, but you'll see in just a few examples that this method is much, much useful when it is a much more complicated inequality. Let's take a look at equation 3x minus 5 equals 0. Solve it like you've done before, and you'll see that x equals 5/3 is your solution. If you look at this inequality, you will see that to solve, add 5 to both sides. Again, solve, and you get x less equals 5/3. This is what we've been doing, and so our solution would be x less equals 5/3. Well, let's review our second method that you just learned. You take the number line now, and it's broken into below 5/3 and above 5/3, and you do test points. So you take the equality, solve it, you get 5/3 as the solution. In this particular case, equal to 0 is allowed or wanted, and so therefore 5/3 is a solution. All right, let's do test points. Pick a number below 5/3, say 0, and you end up with a -5 less equals 0 is a true statement, which means that any number that is smaller than 5/3 is going to make this inequality a true statement. Remember, no matter what number you pick here, 3 times it minus 5 will always give you a negative number. Similarly, if you take a number bigger than 5/3, you'll end up with a false statement because you'll always get positive numbers. So 1 less equals 0 is a false statement when you pick 2 as a test point. False statement means that is not part of your solution. So here's your solution. And so interval notation, -infinity to 5/3, and 5/3 is square bracket because 5/3 is included. All right, let's see now how you can solve this equation. Remember the zero property. If you have a product of two things equaling 0, the only way that's going to happen is either x plus 1 is 0 or x minus 2 is 0, giving you -1 or 2 as solutions to this equation. Let's do an inequality and take a look at x plus 1 times x minus 2 less than 0. If you wanted to undo and do the first method, it's not going to happen here because this is not a linear inequality. And so here, the second method is going to be very useful to you. So again, solve the equality. You end up with -1 and 2 as your solutions, which will make the quantity, the product here, exactly equal to 0. Excuse me. Make the product exactly equal to 0, which you know is going to be false. So -1 and 2 cannot be included, so we have to punch holes there. So now the number line is broken into 3 sections: below -1, between -1 and 2, and above 2. All right, let's take a look at test point below -1, like say -2. When you plug it in, you end up with positive number 4. So 4 less than 0 is going to be a false statement. So none of these numbers are going to work. Let's pick a number between -1 and 2, say 0. And you'll see that this does satisfy the inequality because all numbers above -1 will make this a positive. All numbers are under 2 here. This will make a negative, giving you a negative product, which is exactly what you want. So this is a true statement, so this is part of your solution. Let's pick a number bigger than 2, say 3, plug it in. You're going to get both positive numbers, so the product is going to be positive. So 4 less than 0 in this particular case is a false statement, so none of these numbers are going to work either, and therefore your interval notation will be -1 to 2 is your solution. So even when it looks like you cannot solve an inequality by the methods you used to know, this new test point method will work perfectly. And it doesn't matter whether you have a quadratic or even a non-linear rational inequality you can solve. You just have to remember that in a rational inequality, all places where denominators are 0, you will have to not include in the solution because they make the solution undefined. That's not part of this course, and so we won't do an example of that type, but you can read the textbook because we do an example there. All right, let's take another example here. We saw how to solve absolute value equations before using the distance from 0 stuff. So we'll finish that off. We know that x minus 4 is 5 if and only if distance is 5, if it sits right on 5 or -5, and then add 4 to both sides to give us solutions of -1 and 9. All right, so here's our -1 and 9, our solutions to this equation. Let's do the inequality. In this inequality, solve the equality first, giving you solutions -1 and 9, which we have here. But as you see, we cannot have equal to 5, so we're going to have to punch holes in there, right? -1 and 9 are not solutions. But The number line is now broken into 3 segments: below -1, between -1 and 9, and above 9. So let's do test points, and you will see that here by plugging in -2, you end up with 6 is bigger than 5, which is a false statement or true statement. What do you think? Oh, I already wrote it here, so you can actually see it. But if you were doing it on your own, you can see just plugging in that 6 greater than 5 is a true statement, so that's going to be part of your solution. All right, pause the video here and pick a point between -1 and 9 for test point and see what happens on your own. Assuming you have done that, you will see that no matter what number you pick between -1 and 9, you got a false statement, which would mean that you always got numbers that are smaller than 5. And so, for example, here I picked 0, and 0 gave me 4 as the value of absolute value. 0 minus 4, and 4 is not bigger than 5, so it's a false statement. If you pick a number bigger than 9, say 10, and you got 6, 6 is bigger than 5 is a true statement, so that is part of your solution. And so we can solve this inequality and got solution of -infinity to -1 and 9 to infinity. So you can see how by being able to solve the equation, you can solve the inequality by doing test points. We already know how to solve the equation, so let's say you solve this absolute value equation. Now you do the inequality on your own. Pause the video and see what you can do. So 1/3 and 3 are your solutions. In this case, they are equal to is allowed, so they are included. So for the rest of the solutions, you'll have to do test points. So pick, say, 0. 0 will give me 5 less equals 4, which is a false statement. Whereas if I plug number between 1/3 and 3, say 1, I end up with 2 less equals 4, which is a true statement. So that is part of my solution. If I pick a number bigger than 3, I end up with 7 less equals 4, which is a false statement. So in this particular case, our interval notation will be 1/3 to 3, and 1/3 and 3 are included. So now you can consider doing video log questions. So here are some equations. There are more equations we're going to give you to solve. And then here are some inequalities. And then some more equations.